Hello, welcome to Learning Chemistry with Reba. Today we can discuss the frontier orbital description and Hoffmann description of Diels Alder reaction. Here we have explained what is a Diels Alder reaction. We have given a general introduction to a Diels Alder reaction. We can say a Diels Alder reaction is a reaction between a diene and a dienophile, which is thermally catalyzed to get a cyclic product. So here we can see the diene is butadiene and the dienophile is ethylene. That means the reaction between a 4-pi component system and the 2-pi component system, under thermal condition we get a Diels Alder reaction and a cyclic product. So here we can see that this is a thermally catalyzed, but what happens when it is photochemically catalyzed? When it is photochemical, when this reaction happens in a photochemical condition, the reaction won't take place. That means Diels Alder reaction is thermally allowed, but it is photochemically forbidden. And in this video, we are discussing why it is only thermally allowed and what happens when it under the photochemical conditions. So in general, we can say 4+2 cycloaddition reaction is thermally catalyzed, but it is photochemically forbidden. But we can see, let's see what happens when it comes to a 2+2 cycloaddition reaction. When it comes to a 2+2 cycloaddition, we use a 2-pi component system, and other is also a 2-pi component system. Here we have, we can see an ethylene and a maleic anhydride, both are a 2-pi component system, and the 2-pi component systems are interacting. And when we study it within under heat, that means under thermal condition, no reaction occurs. But when it is studied under UV light, photochemical condition, good reaction occurs. So the 2+2 cycloaddition is opposite to that of 4+2 cycloaddition. To understand this, we have to study the orbital interaction, orbital phenomenon that is occurring under the photochemical and the thermal condition. So, first, before moving into that, we first have to keep in mind 4+2 cycloaddition reaction is a thermally catalyzed, whereas 2+2 cycloaddition reaction is a photochemical catalyzed. In further slides, the following slides, we are going to discuss why this happens. Here, first we can discuss how it happens with the 2+2 cycloaddition reaction. So we have seen the last slide that 2+2 cycloaddition reaction are photochemically allowed and thermally forbidden. So first we are going to see what happens when it is thermally under the thermal condition. We can see this is a 2-pi component system alkene. This is another 2-pi component system alkene. These two undergo 2+2 cycloaddition to get this product. That means this pi bond shifts to here and this to here. And so an added product will be cyclobutane for the 2+2 cycloaddition. But here we can see this is under thermal condition. That means heat is given. So what happens is that this reaction won't take place. And we are now taking the orbital diagram to explain the unfavorable condition of the thermal. So the unfavorable thermal condition. So in the first structure we have ethylene here. This is CH2 double bond CH2. This is an alkene component. This is alkene. It has one pi bond and one sigma bond. So corresponding to the one pi bond, it has a pi molecular orbital, and corresponding to that it has a pi star anti-bonding molecular orbital. So this alkene has a pi orbital and pi star orbital. Pi orbital have no knots, but when it comes to the pi star orbital, it has knots. Okay, it has one knot. For pi, there is no knot, and for the pi star orbital, it has one knot. So also it has a 2 pi electron. This alkene has 2 pi electron. So when these pi and pi star orbitals are arranged in the increasing order of energy, pi orbital is at lower energy than the pi star orbital. So these 2 pi electrons get into this low energy pi bonding molecular orbital. This is pi bonding molecular orbital, and the 2 pi electrons enters to this pi bonding molecular orbital, and the pi star orbital still remains vacant because it has only 2 pi electrons. Since it has only 2 pi electrons, these 2 pi electrons enters to the pi bonding molecular orbital, and thus here this pi molecular orbital forms the HOMO. That means HOMO means highest occupied molecular orbital, above which there is no electron. So this pi bonding molecular orbital is the highest occupied molecular orbital, and therefore this pi star orbital is lowest unoccupied molecular orbital. There are no electrons, so this becomes LUMO, and this becomes HOMO for this alkene. This is same for the next case also for the other alkene. For the other alkene, that is also a 2 pi component system which has 1 pi bond, that is 2 pi electrons. It has 1 pi bond, so it correspondingly has 1 pi bond, pi bonding molecular orbital, and 1 pi anti bonding molecular orbital. And in this, in the normal case, the 2 pi electrons enters to this low energy pi molecular orbital, and thus this forms as a HOMO, and the upper pi star anti-bonding molecular orbital, that is vacant, and that is LUMO for the second alkene. So for the first alkene and the second alkene, it's first 2 pi component, and for the second 2 pi component, both has HOMO as pi molecular orbital and LUMO as pi star molecular orbital. This is the case for heat in the thermal condition. So what happens when these two alkenes interact? The HOMO of one alkene donates electron to the HOMO of the other alkene. This can take place like this or like this. That means in two cases that can take place. That is, HOMO of ethylene gives electrons to the LUMO of the this substituted alkene, or the HOMO of the substituted alkene gives electrons to the LUMO of the other alkene. This depends upon the reaction substituents and conditions. And anyway, in thermal condition, the HOMO and the LUMO interaction takes place. The HOMO of the one alkene interact with the LUMO of the other alkene. Now we can consider what happens with the orbital. So here we can say the HOMO of the one alkene interacts with the HOMO of the other alkene. So we have drawn one HOMO of the one ethane. Let it be like this. The HOMO of this alkene is drawn like this. So with the no knots, and that interact with the LUMO of the another ethane. That this is the another alkene, and here we have the LUMO with the one node. This is shown, one node is there. And when these two pi component system, when these two alkenes approach, we can see that this part is in phase plus plus, but this part is in out of phase plus minus. So this reaction won't takes place. So that is why under the thermal condition, what happens in the thermal condition, 2 plus 2 cycle addition proceeds only by the interaction between the HOMO of one alkene and the LUMO of the other alkene. But the one will be in phase and other will be out of phase, and hence this under thermal condition, this reaction could not proceed. Okay, but what happens under photochemical condition? We can say in photochemical condition, one of the two reactants, here we have alkene simple ethene, and here we have another substituted alkene. Under thermal condition, this is the heat condition, and this won't take place because one is in phase and the other is out of phase. But when under photochemical condition, we are going to see what happens under photochemical condition. We have 2 pi component system, two pi component system. From these two components, one of the component, here it is considered as the substituted component. From these two components, one of the component under photochemical condition get excited. It undergo excitation. So the alkene component stays in the ground state, whereas the substituted alkene component get excited under photochemical condition. So since the alkene is in the ground state, the orbital diagram will be like this as such. That means 2 electrons enters into the home of the alkene, and the LUMO of this simple alkene do not have any electron. This is like the same, but when it comes to the substituted alkene, under photochemical condition it get excited. What happened? When it was in ground state, it also has one pi bond, so corresponding pi molecular orbital, and correspondingly pi star antibonding molecular orbital. In the normal state, the 2 pi electrons enters to this pi orbital. But when it get excited, one of the electron from the HOMO, that means pi orbital, get shifted to the LUMO of the same component. Here we can see for this alkene component, the initial HOMO pi molecular orbital gave one of the electron to the pi star orbital under the light photochemical excitation. So here we can see the pi orbital has one electron, and the pi star orbital now has under photochemical condition have the another electron. So earlier for this alkene, the HOMO was pi, and after the excitation, the new HOMO is the pi star. So, under photochemical condition, the simple alkene component has HOMO pi, and the substituted alkene has the HOMO pi star. Now, these two interact. That means the HOMO of the photochemically excited alkene, the HOMO of the photochemically excited ethene. That is, this is the HOMO of the photochemically excited ethene, which has one knot plus minus that is shown here, and it interacts with the HOMO of the excited alkene, interacts with the LUMO of the ground state alkene, the other alkene. The HOMO combines with the LUMO, and the interaction happens between. What is the LUMO of the other alkene? This is the LUMO of the other alkene. This also has one knot. So in the photochemical excited state, the new HOMO of the excited alkene and the LUMO of the unexcited alkene both have one knot. So when these both interacts, they both are in phase, and this reaction proceeds smoothly. And that is why 2 plus 2 cycloaddition reaction is favorable under photochemical condition only. In the thermal condition, in the heat condition, the HOMO of the one alkene interacts with the LUMO of the other alkene. That means pi interacts with the pi star, and hence one will be in phase and other will be out of phase. But when it comes to the photochemical condition, the HOMO of the one alkene, the HOMO of the one alkene, that means excited alkene pi star, interacts with the LUMO of the unexcited alkene. Both are pi star orbitals. The HOMO of the excited alkene interacts with the LUMO of the unexcited alkene. That is also pi star. So both has one knot, and when it comes towards each other, it undergoes an in-phase interaction, and hence the both are in phase. Since both are in phase, this reaction proceeds smoothly. So 2 plus 2 cycloaddition reaction is a photochemically catalyzed reaction. And now we can see what happens when it comes to a 4 plus 2 cycloaddition reaction. Same like for 2 plus 2 cycloaddition reaction. In 4 plus 2 cycloaddition, one component is a 4 pi component system. That is, we have seen a butadiene, and the other component is a 2 pi component system. Here it is taken as malic anhydride. So this is the molecular orbital diagram for the butadiene. Here for the butadiene, it has how many pi electrons? It has 4 pi electrons. For butadiene, it has 4 pi electrons, hence psi 1, psi 2, psi 3, psi 4. That means it has 2 pi orbitals and 2 antibonding pi orbitals. So in butadiene, we have 2 bonding molecular orbitals and 2 antibonding molecular orbitals. Antibonding molecular orbitals stands at a higher energy than the bonding molecular orbitals. And in butadiene, we have a psi 1, psi 2, psi 3, psi 4 as the bonding molecular orbitals. In butadiene, we have 4 pi electrons, and we know that as per the molecular orbital theory, each molecular orbital can accommodate only 2 electrons. Since there in butadiene there are 4 pi electrons, 2 of the electron enters to the lowest molecular orbital psi1, and the other 2 enters to the next high molecular orbital psi2. So altogether there are 4 pi electrons. And now we can see this is for the butadiene, and now we can see that the HOMO of the butadiene is psi2, whereas the LUMO of the diene is psi3. No, with no electrons. This is the LUMO, lowest unoccupied molecular orbital. That means the molecular orbital with no electrons, and it is at a lower energy. These are the two molecular orbitals with a low energy, with no electron, and this is the lowest occupied. Hence, this is the LUMO, and this is the highest occupied molecular orbital. That means highest molecular orbital with electrons. So, in normal condition, that means in thermal condition, that is the normal condition, the HOMO of the diene is psi2 and the LUMO of the diene is psi3. And in the normal condition, what happens with the Malic anhydride? Malic anhydride is a 2 pi component system, and there is only 1 pi bond or 2 pi electrons, so it has pi and pi star. So this is the pi with no node, and this is the pi star with 1 node. Here in psi1 there is no node, in psi2 there is 1 node. Here we can see here it is 1 node, and in psi3 we can see 2 node, here 1 and here 1, so 2 node. In psi4 we can see 3 nodes, 1, 2 and 3. So under thermal condition, the HOMO of the diene is psi2 and the LUMO of the diene of phi, that means Malic anhydride, is pi star with no electron. The HOMO interacts with the LUMO. Also, there is another chance, the HOMO of the anhydride diene of phi, that means this pi orbital, interacts with the LUMO of the diene, that is psi3. There are 2 chances to occur. What happens when the LUMO of the anhydride, this is the first case that is shown here, the LUMO of the anhydride is given here and it interacts with the HOMO of the diene. We can see the HOMO of the diene here, and again we have drawn the orbital diagram, and we can see that both are in phase interaction, of course, 90-90 and positive. So this is allowed. And what happens when the HOMO of the anhydride interacts with the LUMO of the diene? Anything in any way it can take place. So here we can see the LUMO of the diene, that is psi3 orbital, and the HOMO of the anhydride, that is pi orbital. Here also they are in phase. So there are 2 chances for the interaction between 4 pi component system and 2 pi component system. That means there are 2 chances of interaction, the Diels Alder reaction. But the most preferred chance is this one, that is the HOMO of the diene. The HOMO of the diene interacts with the LUMO of the diene. That is the most preferred because there is only a small energy gap between the psi2 and pi star. That is, there is only a small energy gap between the HOMO of the diene and the LUMO of the anhydride, and hence the interaction is maximum here. That means the orbital interaction is maximum here, and hence this interaction is more favored. That means the interaction between the HOMO of the diene and the LUMO of the anhydride. Next video we have said that the diene reactivity can be increased by electron releasing group, and the dienophile interactivity can be increased by the electron withdrawing group. Here, if an electron releasing group is attached to this diene, the energy of this I2 increases from here. When the electron density increases in this diene by the substitution with some electron releasing group, the energy increases. Whereas when The dienophile, when it is substituted with electron withdrawing group, as we have discussed in the last video, here the energy decreases. That means the electron density decreases in the pi bond and hence the energy decreases. So when the diene is substituted using an electron releasing group and when a dienophile is substituted with an electron withdrawing group, the HOMO of the diene increases its energy whereas the LUMO of the diene decreases its energy. Hence, further the energy gap will become further smaller and then the Diels Alder reaction could proceed more easily. So that is why it is said that a Diels Alder reaction is more favored by the substitution of diene with electron releasing group and the substitution of dienophile with an electron withdrawing group. Thereby which we can decrease the energy gap between the HOMO of the diene and the LUMO of the anhydride or dienophile. Thus the Diels Alder reaction is favored under thermal condition. And what happens if when it is photochemically catalyzed? If when it is photochemically catalyzed, one of the electron goes to here. One of the electron goes to here and Psi3 now becomes the HOMO of this diene and this HOMO interacts with this LUMO. But we know that when this Psi3 interacts with this, it is not orbitally favored. That means one will be in phase. This one and this one will be in phase. The other one will be out of phase. Hence, the photochemical condition is not fair. In photochemical condition, excitation of electron takes place and Psi3 becomes the HOMO. When it combines with this pi star LUMO of the anhydride, that orbital interaction, one will be out of phase and hence the photochemical condition is not preferred. Only thermal condition is preferred with the interaction of a low energy LUMO of the dienophile. That means, which means when the dienophile is substituted with an electron withdrawing group, the LUMO get decreased. Energy of LUMO get decreased and high energy HOMO of diene. The HOMO of the diene energy can be increased by electron withdrawing group, thereby the energy of Psi2 increases. That means high energy HOMO and low energy LUMO. These two interacts to get the Diels Alder reaction under thermal condition. So here it is given the further explanation. That means simple alkene have a high energy LUMO. We have seen that simple alkene have a high energy LUMO, but when it is substituted with an electron withdrawing group, what happens? The LUMO, the energy of the LUMO of the dienophile decreases. Whereas the diene react easily with the electrophilic conjugated dienophiles like those substituted with electron withdrawing group like carbonyl or nitro or any other electron withdrawing group. Therefore, Diels Alder reaction occurs between an electron rich diene and electron poor dienophile. Now we can discuss the dimerization of dienes. For that, we have taken two molecules of butadiene and they are subjected for thermal condition, subjected at a thermal condition. And we are looking forward for a cycloaddition reaction. Two chances are there since we have taken a 4-pi component system. Both are 4-pi component system. There are two chances. There is a chance for 4+2 cycloaddition. Also, there is a chance for the 4+4 cycloaddition reaction. But the most favored is a 4+2 cycloaddition. We can see what's the reason behind it. So, here in the 4+2 cycloaddition under thermal condition, one of the butadiene acts as a 4-pi system and the other butadiene acts as a 2-pi system. So, here in this 4-pi butadiene system, the HOMO is Psi2. We know that from the last slide, we know that the HOMO of a diene is Psi2 and this is the HOMO Psi2. With one node and the other that HOMO interacts with the LUMO of the next butadiene and we know that the LUMO for the butadiene under thermal condition is Psi3 and this is the Psi3 orbital for the second butadiene with the two nodes here and these two interacts, the HOMO of one diene interacts with the LUMO of another diene, but the interaction of the second butadiene is only with the two carbon centers that is drawn here and these when they both interact, we can see that both sides give a bonding interaction. So this reaction is favored. 4+2 cycloaddition is favored to get this product. So we know that dimerization of diene occurs via a 4+2 cycloaddition under thermal condition. But what happens when it comes with a 4+4 cycloaddition? Here also we know that the HOMO of one diene interacts with the LUMO of the other diene, and we know the HOMO of one diene is Psi2 and the LUMO of the other diene is Psi3, and when same like this, when both interacts but through 4 carbon atoms. This both butadiene acts as a 4-pi system, and we can see here that one is bonding but the other is anti-bonding. So this reaction is not favored. So the dimerization of diene is unfavored under thermal condition via 4+4 cycloaddition reaction. But we can synthesize this cyclooctadiene from 2 butadiene molecule via the alternative method is via transition metal catalysis, and also the other method, one is transition metal catalysis and the other is photochemically catalyzed 4+4 cycloaddition reaction, which means under photochemical condition the HOMO of the one diene changes from Psi2 to Psi3. That means one electron from the Psi2 excites to Psi3 and Psi3 now becomes the new HOMO of the one diene, and that Psi3 new HOMO of this diene interacts with the LUMO of this diene. LUMO is itself Psi3 and both the Psi3 interacts, and this is not the diagram, but we can imagine that when two Psi3 interacts, here in both sides bonding interaction occurs, and hence this dimerization is favored under this 4+4 cycloaddition. Dimerization is favored under photochemical condition, but it is unfavored under thermal condition. So in conclusion, we can say dimerization of dienes via Diels Alder reaction occurs here. Next we have to look what is the effect of Lewis acid in Diels Alder reaction. Look, we have said that the introduction of any electron releasing group to the diene structure. The introduction of any electron releasing group to the diene structure increases the energy of HOMO, that is Psi2. Whereas the introduction of any electron withdrawing group to the dienophile decreases the energy of the LUMO, and thereby it decreases the energy gap and the reaction get failed. And here we are discussing what happens if we use a Lewis acid in Diels Alder reaction. When a Lewis acid like SnCl4 is used, it interacts with the carbonyl group of this dienophile, and that means since this is a Lewis acid, the oxygen donates its electron to this SnCl4, thereby giving a more powerfully, and thus this carbonyl group becomes more electron withdrawing group than this. By the introduction of this Lewis acid, this substituent becomes more powerfully electron withdrawing, and but thereby the LUMO of this alkene, that means the pi star orbital of this alkene, the energy get decreased. The energy of this alkene decreases, while due to the introduction of this electron releasing group, this is an methyl group, by the introduction of this, the HOMO of this diene increases, thereby the energy gap decreases. And we can say without a Lewis acid, that means here it is heated into olivine, that's not a Lewis acid. So without in the absence of Lewis acid, the yield is 71:29. This is the in the next video we can discuss the regioselectivity of Diels Alder, and this is the major product. Ortho-para relation is the major product that we can see. Here we can see here we can see in the absence of Lewis acid, the yield is 71%. The yield of this regioselectivity product is 71%, but in the presence of this Lewis acid, it has increased to 93%. That means with the introduction of this Lewis acid, the electron withdrawing capability of the substituent increased, and hence the energy pi star energy, that means LUMO of the dienophile decreased. The energy of the HOMO of the diene, the energy of the HOMO of the diene side 2 increased, and thereby the energy gap decreased, which favored the smooth execution of this Diels Alder reaction. So the effect of Lewis acid means the Lewis acid increases the yield of the Diels Alder reaction, or Lewis acid favors Diels Alder. These are all about these are the frontier molecular orbital description. Now we are moving to the Woodward-Hoffmann description. This is quite complicated, but we can see some uh, conclusion for this Woodward-Hoffmann description in a nutshell. But this is more complicated than the frontier molecular orbital. As per the Woodward-Hoffmann rule, a thermal pericyclic reaction, it means the pericyclic reaction which is favored by thermal condition, is allowed when the total number of 4Q plus 2 suprafacial component and 4R anterofacial component must be odd. That means in Diels Alder reaction, consider Diels Alder reaction, we have a diene and an alkene. Diene, we know it is a 4-pi component system, whereas alkene, the dienophile, is a 2-pi component system. The diene is a 4-pi component system, and thereby we know that it's a 4R type. That means we know in case for the aromatic Huckel theory for the aromatic compound, we know that 2, 6, 10 electrons, there are 4 and plus 2 electrons, whereas 4, 8, 12, there are multiples of 4 electrons. If it has a multiple of 4 electrons, multiple of 4 as the number of pi electron, that is anti-aromatic. We have seen that. Here, this is, since this is a 4-pi component system, this is a 4R type. That means 4 into some multiple. R is some integer. 4 into 1, 4. 4 into 2, 8. That is, if the diene is a 4-pi component system, so this is a 4R type. That means 4 into 1, that is 4. And so this diene is a 4R type, whereas alkene is a 2-pi component system, and we know that that is 4Q plus 2. That means Q is an integer, 4 into 0 plus 2. So this 2-pi component system is a 4Q plus 2 type, whereas 4-pi component system is a 4R type. Just like the Huckel rule, 4n plus 2 and 4n systems. So, what is said by Woodward and Hoffmann by this rule is that for a thermal pericyclic reaction, the number of 4Q plus 2 system, the number of 2-pi component system, the number of 2-pi component system plus the number of 4-pi component system must be odd. Here we can see the number of suprafacial, 4Q, S stands for suprafacial and A stands for anterofacial. As per Woodward-Hoffmann rule, in an allowed thermal pericyclic reaction, the number of suprafacial 4Q plus 2 component plus the number of anterofacial 4R components with a 0, 4, 8 electron multiples of 4 should be an odd number. This is a Woodward-Hoffmann description. We can see with the example. Here we can see the Woodward-Hoffmann description for the Diels Alder reaction. This is an example. Here we can see this is a 4-pi component system. That means 4-pi component system means it has 4-pi electrons. So this diene is a 4-pi component. And this is an alkene, this is a 2-pi component, that means 4Q plus 2 S system. This is a 4Q plus 2 system. Since this is a 4-pi component, this is 4RA system. And we have to know whether this is allowed or thermally allowed or not. So, when this reaction is given, first look for how many 4Q plus 2 component system, how many 4Q plus 2S. There is only one 4Q plus 2. And next, look how many 4RA system. That means 4-pi. There is only one 4 pi component, but this is ultrafission. We know that we have studied that the interaction both in both sides thermally catalyzed, that is suprafission interaction. They both are in phase. So there is no 4R ultrafission. This is 4R suprafission, pi 4. This is 4R suprafission, and this is 4Q plus 2 suprafission. There is no 4R ultrafission. Therefore, there is one 4Q plus 2 component acting and no 4RA component. So total 1 plus 0, that is 1. So since this is an 1 is an odd number, it is an allowed transition. This is quite complicated, but the one thing we have to keep in mind is that when a reaction is given and when we have to look whether this is a thermally allowed pericyclic reaction, first we have to look for a 4 pi component system, and then we have to look for a 2 pi component system, and we have to calculate how many 4 pi component system. There is only one 4 pi component system, and there is only one 2 pi component system. And then next we have to look whether it is suprafission or ultrafission. We know that these both are suprafissional component. So 4RA is 0. There is no ultrafission 4 pi system, therefore that is 0. But it has a 4Q plus 2 suprafissional component. So that is only 1. 1 plus 0, that is 1. That means 1 is an odd number, so it is allowed transition. These are all about the orbital consideration, frontier molecular orbital consideration, and Woodward-Hoffmann description for the Diels Alder reaction. Hope you all enjoyed the video. Thank you.